So, usually we believe in Newtonian mechanics, and we have followed it and we are following it, and so we follow the law of gravitational forces, and we know that any object is pulled by a force which is called gravitational force, and this idea was given by Newton and it works very fine. But if you follow general theory of relativity, then there is no such force of gravity, and things are not pulled by any force which is gravitational. It is just that the massive objects, they appear to warp the space and time fabric, and that is why there is a curvature, and that is why it appears that objects are coming towards the massive object because there is a curvature in the space time fabric. And this idea is very astonishing because in the general theory of relativity, so if you have a massive object which can be sun, it can be earth or something, and the space time curvature will be curved near this object, and because it is curved, any other object which will be coming in the straight line will appear to go in a curvature, although the object will be moving in straight line only. So, and this will be happening, and the curvature will depend upon how massive is the object we are talking about. So, for instance, if you follow, and we have divided Earth in latitude and longitudes. So, if you follow two straight lines on a curved surface, so on Earth so this will be like this. So, these two lines are completely straight lines on the Earth. So, you can take an example of longitude, and these two lines are straight, and if you are walking on following these two lines, you are walking straight at any point of time, but because the surface of the Earth is curved, these straight line will meet at some point of time. So, usually the idea is the straight lines meet at infinity, meaning that they never meet, but if the surface is curved, then these straight lines will meet at a certain point, because the surface is curved on which the line is drawn. So, in a way these lines are actually not straight, but here we can see the surface, and we are still talking about only space and not time. And when you take general theory of relativity into consideration, you take, so this fabric which looks like a two-dimensional thing is not only including the three-dimensional space field, but it also has the time involved in it. So, again, not only a moving mass becomes energy, or static energy becomes mass, it is also that the time itself slows down if you are moving with a very high velocity, or if you are close to a very massive object. So, here not only the space is curved, but also the time is curved. So, the time here and time there will be different, and this is known. So, with this concept it comes, and before also the theory of relativity, it is known to us, at least in the field of materials, that time plays an important role. But fortunately or unfortunately, we have started with some materials to begin with in the history of humans, which happen to be metallic materials, and these metallic materials are at room temperature, at least they do not show the effect of time in a short span we have, but that does not, or we should not ignore the effect of time. So, time plays a very important role in the deformation also, and therefore Recently we started working with materials which are non-metallic. So we started working with polymers, we started working with ceramics, and a whole different regime of material opened up in the new era. And so the problem or the solution both is this, that material scientists, they developed all the theories on metallic materials. And once we started working with polymers or biomaterials, we started with the same concept and we are correcting it. Even now, we are trying to correct it so that it becomes applicable to those materials which are non-metallic. And there we have to include the effect of time. So, we will talk about what is the effect of time on metallic materials, and you will get a glimpse that when this time effect is very high, then those materials usually are non-metallic, but they show the same effect what we will be trying to understand in context with the metallic materials. Those same effect will be to a higher degree in polymers and in biological materials which are also mostly polymers. So, we are going to understand the time dependent behavior, and this time dependent behavior has various dimensions, has various degrees, and we will talk about those in brief. So, first we should think that how the deformation occurs. So, if I have a tensile specimen and I am pulling this specimen from the upper end, then I am applying some amount of stress and the material is deforming, and material is deforming via dislocations and defects, and at the end you have necking and you have damage and the material fades. But the very core of this deformation is the movement of atoms. So, the atoms are flowing, and you can imagine this deformation in solid to be the movement of atoms in a very viscous material. So, if a liquid becomes very viscous, then you will see similar behavior what happens in solid. However, the difference would be if the solid becomes crystalline. So, if the solid becomes crystalline, you create more and more constraint on the way atoms can move, and that is the concept of dislocations, which we have touched briefly. And if it is non-crystalline, if it is amorphous, then amorphous material behave very close to a very viscous liquid, and we have seen that also experimentally. So, it is not just a theory, but it is proven experimentally that solid, if it is not crystalline, it is a liquid which is very viscous. And therefore, and what is viscosity? So, if you keep semi solid, probably the best example will be the pitch which you use on the streets to you have seen that they heat the concrete and then they make pitch out of it, and then they put it on the floor on the streets. And if you take a piece of that pitch and give it a shape, okay, so give it a shape like a cylinder and keep it, and you go somewhere and come after 2 hours, and this whole thing will be flown on the surface. So, it will be taking this shape. Okay. So, what has happened, you do this you put a drop of water on the surface and the same thing will happen. So, a drop falls on the surface and it instantly takes this shape. This process, what happens with the pitch, is a very slow process or a very slow manifestation of the same process in this case. So, what have we done? We have actually slowed down the time of this process in this case, and that is why you see change from A position to B position in 2 hours or 3 hours, and this you cannot even see because this will take less than a fraction of a second to behave in this way. So, the end product will be instant. So, again the process of going from A to B, how much time it takes, that defines the material property, and it gives us an advantage or disadvantage to utilize that behavior of the material. Okay. So, what is happening is that you have atoms, and these atoms will be moving once you apply stress. Once you apply stress, you are actually pulling the material, and the material is trying to be in its own configuration. It is trying to be next to the atom it was, and it does not want to move. So, they do not want to move because they are in equilibrium state, and if you move them apart, it will take some energy, and that energy is being provided in terms of mechanical energy, and at the end of the day these atoms are moving, and these atoms are moving, and that movement is time dependent. So, if you pull it so fast that you do not allow the atoms to move, so if an atom has to go from this place to that place, it will take some time, and if you do not allow that much amount of time, then you cannot deform it to that extent for the same amount of stress you apply. So, let us understand this in a mechanical way, in a mechanics of materials way, for example. So, what happens is that, let us say that I am applying some amount of stress on a material, and this is my time axis, okay, and this is my strain axis. So, at a very instant, I just take a piece of wire or a chain, and I put a heavy block of, let us say, 20 kilogram on that, and I just hang it. Instantly I hang it, and that much amount of load, so 20 kgf load, so 20 into 10, 200 Newton approximately, no, it will be 200 kilonewton will be applied on that chain or wire, and that amount of force is applied instantly. Okay. So, I have not allowed much time for the material, for the chain to deform. So, what will happen is that there will be an instantaneous strain. Okay. So, at t is equal to 0, some amount of strain will be realized in the material, and let us call it E1, and then you leave it. Okay. So, I have a wire or a chain of, so for simplicity let us take wire. You can compare it to the experiments of Leonardo da Vinci. So, you have wire, and then you hang a bucket, and this bucket has some sand in it. Okay. So, of course, you have some amount of load, and as soon as you hang it, the wire extends by certain amount, and this is my instantaneous strain, and then you leave it and you go somewhere and come back, let us say after 24 hours. Do you think that the wire will be in this final position? The reality is that wire will be extending further. Okay. And we are not talking about plasticity at this moment, we are talking about elasticity. Okay. So, we are talking about effect of time. This has happened at t is equal to t naught, and this will happen, let us say, at t is equal to t1, and in this amount of time a little bit of extension in the wire has happened, and that has happened because now atoms have time to move. You have given it some time, the load is same, you are not changing it, so the material has deformed more. You will get the same amount of strain what you get at t is equal to t1 if you apply this load in the first place very slowly. So, you put this bucket and you leave it. So, let us say if it is 20 kg, then you apply the load in 20 kg in, let us say, 24 hours, okay, or let us say 20 hours. So, you apply 1 kg in each hour. You apply this much load in each hour and keep increasing it until it reaches 20. So, the final point is same, you are reaching 20 kg, but you are taking 20 hours in order to reach there, and you are allowing the material to have its own time, so take its own time. And in that case the strain will be different because the material is getting adjusted every time. So, this is kind of an isothermal process. So, in this case atoms are finding their new equilibrium position, right, and that so the other meaning of this is when the instant load is applied, the atoms are not in equilibrium position, and this will cause a change in their own temperature. Okay. So, this process where the instant load is applied, the entropy of the system is not allowed to change because you have not given sufficient amount of time for the atoms to gain a new configuration. So, configurational entropy has not changed. Okay. So, now if you think that there is no thermal entropy and the total entropy is governed only by the configurational entropy, then that has not changed in this process, in this instant process. So, the outcome of that will be a change in temperature. Okay. And so, and that change in temperature which happens because of this sudden process can be given for metallic materials in this form. So, delta T, where T is temperature, and delta epsilon. So, differentiation of temperature with respect to strain can be given by negative of the molar volume of the material into linear coefficient of thermal expansion, or coefficient of linear thermal expansion into elastic modulus into temperature divided by the specific heat of the material at constant volume. Okay. So, from this equation what is visible is that if you change the strain in positive way, then the temperature will be negative, right. If this is positive, this is positive, then Vm is positive, alpha is positive, elastic modulus is positive, Cv is positive. So, the temperature change is going to be negative, and if you apply compression, then the temperature change will be positive. So, what happens is that if you apply instantaneous load and the material deforms, what happens is that the temperature of the material decreases. So, from the system, the temperature from the environment, the system will have a lower temperature, and if you allow the time, then the strain will recover to what you should have if you allow sufficient amount of time. So, here, and this will allow the temperature to be equalized from the ambience, and therefore, it will come to the isothermal state. So, here it is adiabatic. So, here there is no change in heat of the system, and if you allow the system to relax, then there will be, so the end product will be isothermal. Okay. So, this phenomena is called elastic after effect, and this change in strain because of time is called inelastic strain. So, that process, I should describe it to completion. So, let us say at t is equal to 0, you apply a certain amount of strain instantly. So, that is E1, and then you allow it some time, and in that time the strain will increase following some behavior. It could be linear, it could be non-linear. So, it will increase to the isothermal point. So, the atoms have found its new configuration, and then so it has reached here at, let us say, time is equal to T1. Okay. And from here, if you unload suddenly, so suddenly you cut the bucket. So, the bucket has dropped and the wire, so now here you cut the bucket and the wire is now free, but that process has also happened suddenly. So, what will happen is that the instantaneous strain will come back. So, this much amount of strain will be recovered instantaneously. So, what comes back instantaneously is E1, and then it will take some time to come back to 0, because we are talking about elastic problem only. So, we are not talking about plasticity. This will happen in plasticity also, but that is a little complicated. So let us understand this in elastic process, and then we will go back to the permanent deformation. Okay. So, this is what will happen. A sudden unloading will cause an instant strain recovery of E1, and then certain amount of strain, which is your complete strain, is, let us say, so this is your complete strain, and that is, let us say, E2. So, this much amount of strain is, so from here to here, so this much amount of strain is E2 minus E1. Okay. So this effect is coming purely because of the time effect. Okay. And if we look at the material's deformation, what we have talked about in the stress strain curve, so we apply stress and we apply strain, and we have discussed this in the tensile test, that if you increase the strain rate, so let us say this is the behavior of the material, and then you increase the strain rate and the material deforms in a different way. And usually with an increase in strain rate, you see an increase in yield strength and you see a total decrease in the ductility of the material. This happens because you are not allowing atoms to move, you are not giving sufficient amount of time for the atoms to move. So, their resistance will decrease towards the deformation, because you are not allowing the atoms to deform, you are not allowing the dislocations have certain velocity, right, and that is dependent on strain, if you remember this equation. So, strain rate is proportional to the Burgers vector, the velocity of dislocation and dislocation density. So, the velocity of dislocation, of course, if you change the strain rate, that means if you allow less amount of time, if you increase the strain rate, so that means you are allowing, let us say, some amount 10% of strain in 1 second in comparison to 2% of strain in 1 second. So, you are deforming, you are trying to deform the material more in less amount of time. What will happen to the dislocation velocity? They should increase. If they do not, then it will damage and fail, because material is not able to respond to the load you are applying. What we did not discuss in the tensile test was this, that we said that so I drew something like this. The difference is the elastic modulus was not changing, and this happens when the change in strain rate in comparison to the real metallic behavior is very small. Okay. So, usually we do testing at, let us say, 10 to the power minus 6 per second strain rate. Okay. So, 1 into 10 to the power minus 6 strain rate, then you increase it to 10 to the power minus 4 strain rate, then you increase it to 10, then you can go higher and higher. And here in this region you will not find significant amount of difference in metallic materials in elastic modulus. But if you change, and if you change it from 1 into 10 to the power minus 6 per second to 5 into 10 to the power minus 6 per second, you will not see any change in any part of this stress strain diagram. So, strain rate does not change, does not result in any effect if you do not change it by considerable amount, and this is true for metallic materials. The reason is metallic material show the time dependency very insignificantly. So, the time required for metallic materials to show the time dependence is very high, and this is why the bridges will not deform just because of the time dependence in, let us say, 100 years. But if you keep it there for 10,000 years, those bridges will probably collapse, or at least they will bend. So that is the amount of time which is required for the metallic materials, especially steel, to show the dependence of the deformation on time. They will deform, and that deformation is little different. So that is the deformation where we are going. Okay. So we are talking about time dependent deformation of the material, which is a little different from what we are discussing now. This is what we are discussing here. You can see it in a very small amount of time difference also. So you can actually see it in a wire and bucket experiment, a wire made up of steel. You can see this effect. But the difference in the time what we are talking about, so the strain rate difference has to be very high. If you change it by very minimum amount, and this amount is very minimum, and if you so this is obviously small, but even if you change it from, let's say, 10 millimeter per second to 100 millimeter per second, you will see very minimal difference. The difference probably will be significant if you change by an order of 100. So 1000 meter per second will obviously show you difference in the stress strain diagram. But elastic modulus will still not change significantly for metallic materials. But elastic modulus will change. It's not that it is not changing, it is changing, but by a very, very small amount. Okay. So, but the same effect will be very high if you do polymer testing, because they show this time dependence, and so the required time for polymers to show this dependence is very small. And you can see this effect by stretching a polymer. You stretch the polymer and it will become cold, it will become cooler. You can see the temperature effect in the polymers. But in metallic materials, you will not be able to realize the temperature effect by your hands, which will be true for polymers. But of course, a thermocouple will show you a difference. Okay. So this is what we are going towards. We are going to talk about time dependent behavior of the material. Okay. So here what we talk about is called the thermoelastic effect. So this what we talked about, that there is a change in temperature and there is a change in elastic strain if you allow the time, is called thermoelastic effect. And this is different from what we are going to talk about, because we are not only going to talk about elastic effect, we are going to talk about deformation which is permanent and which is time dependent. Okay. So this is not creep, this is thermoelastic effect. There is something called viscoelasticity, again which is similar to this. So the elastic strains or elastic deformation is significantly time dependent, and then it is viscoelastic. And when plastic deformation becomes time dependent, it is called viscoplasticity. We will not talk about those mechanisms, but you should know that the plastic deformation what we have talked about is also time dependent. Any phenomena which happens in this universe has to be time dependent. All right. Okay, so now let us talk about creep.